Okay, all right, students. Welcome back. Yeah, this is this. I want to give you the solution to the NECO Physics that was written in 2021. Okay, and I started with the objective parts of that NECO Physics 2021, and then part one I was able to solve 1 to 20. I've uploaded the video. Part 2 I was able to solve 21 to 40, and this is part 3. This is part 3, which will be 41 to 60. Okay, so I broke it down into 3 parts. So today we are going to look at the part 3, that is solving from 41 to 60 of the objective part. So part 4 will be the theory part of that NECO. Okay, the analysis of the questions here, the solutions of the questions to NECO, as I always tell you, will also help you to pass your WAEC, will help you to pass your JAM, will help you to pass other exams that has to do with physics. Okay, and it will give you intro into A-level physics. Okay, so as I've told you that I'm also into other subjects like chemistry, maths, further maths, technical drawing, that you can just like call me for that or WhatsApp me for that for private teaching. Okay, WhatsApp me on 09074526311. WhatsApp or call for private lesson at any of the exams, WAEC, JAM, common entrance and all that. All right, so let's start. Let's see the solutions to part 1, to part 3, that is solving from 41 to 60 of the NECO. This year 2021, as I told you in part 1, in part 2 of this my video, that NECO was written before WAEC. Are you there? So, and once you go through these, you're able to pass your WAEC that is forthcoming maybe in the next 1 month or so. Don't forget to click on the subscribe button and the likes, okay, so I see the previous videos. If you don't click on subscribe button, you not see the previous video, which is part 1, part 2, and the subsequent one, which is part 4 for the theory aspect. Okay, all right, let's start. My 41 question says, all right, which of the following elements crystal is face-centered cubic? Which of the following element crystal is face-centered cubic? We have option A, beryllium, option B, copper, option C, magnesium, option D, sodium, option E, zinc. Which of the following element crystal is face-centered cubic? So you have types of crystals. We have the body-centered centered cubic. We have body-centered cubic. We have face-centered cubic, and we have hexagonal close packing. These are 3 types of crystals: body-centered cubic, face-centered cubic, and hexagonal close packing. Okay, so the body-centered cubic is just like this. Any crystal that is just draw a cube in primary that you've drawn in primary school. Okay, so whenever we have identical crystals at each of the corners, we have identical particles. The particles are ions. Are you there? We have like sodium ions, chloride ions. Are you there? So we have sodium ions and chloride ions. We have it at each of the corners. Are you there? And then we now have another one at the center of the cube. the center of the core. So this is body center cubic. So, and this one we virtually join to this, 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 join to this. So this is body center cubic crystal. Okay, so and examples of these are iron, salt of iron, salt of iron, chromium, platinum, etc. Salts, that is iron salt, chromium salt, platinum salt. These are examples of body center cubic. But face center cubic and the rest. Face center cubic, you still have your cube. You have your cube. Are you there? You have a crystal will be in form of this. Are you there? When a crystal is in form of this, and there are identical ions, identical particles, ions. Are you there? At each of the corners. Don't forget that there's another one here. At each of the corners. Okay, there's another one here. Then, so we have identical particles, identical ions at each of the corners. Are you there? Then we now have that same identical particles at each of the faces. You know, it has 6 faces. 6 faces. You put one. You know, it has 6 faces. You put another particle at each of the faces, apart from each of the corners. This face is taking 1. The face that is opposite this one is taking another 1, taking 2. Then this face is taking 3. Are you there? So the face that is facing this other face, the face that is facing it, okay, I wish it has 4. Are you there? Then we have up and down, 5, down, 5, up, 6. Okay, so when you have it this way, it is face center cubic. For face center cubic, they are just those elements that are around hydrogen. When it comes to reactivity series in chemistry, okay, just like lead, they are metals, they are common metals. Okay, these are lead, copper. Okay, copper, silver. Okay, those elements around very close to hydrogen and below hydrogen. Those elements that are very close to hydrogen and below hydrogen, lead, copper, silver, common metals like that. Okay, face center cubic. Then we have hexagonal close packing. That is hexagon, 6-sided. So you join 2 hexagons together. Okay, when you join them together, you join this. So this is hexagonal close packing. So it's another type of crystals: body center cubic, face center cubic, and hexagonal close packing. But that was just by the way. Our main focus here is face center cubic, FCC. So which one is the correct answer? Option A, beryllium. Option B, copper. Option C, magnesium. Option D, sodium. Option E, zinc. You can see that B, the FCC, copper is there. So we have 41B, and 41 is B. Now 42. Below is a list of substances. We are given glycerine. Okay, we are given glycerine. We are given grease, and we are given kerosene. Okay, kerosene. So that said, below is a list of substances. Which of the arrangement is in increasing order of viscosity? Which of the arrangement is in increasing order of viscosity? We should arrange it in order of how viscous they are. In order of, to a layman, in order of thickness. Okay, so viscosity is the internal friction acting in the layers of a fluid in motion. Okay, is the internal friction acting in the layers of a fluid in motion. Fluid means liquid or a gas. Are you there? So look at your water, look at water, look at palm oil. Do you understand? Look at grease. Grease is the thickest. So look at this now: glycerine, grease, and kerosene. So we should arrange them in order of what? Increasing order of viscosity. That is, from the one that is least viscous to the moderate one, then to the highest one, the one that is most viscous. That is thickest, the thickest. If you look at grease, if you pour grease from its container, it comes out slowly. Are you there? So grease will be the most viscous. So grease is the last one. Then the middle one will be glycerine. Glycerine, because glycerine is from glycerol, and glycerol in chemistry is propan 1,2,3-triol. Propan 1,2,3-triol. Around 1,2,3-triol has three hydroxy groups. So it makes the three hydroxy groups make the glycerol, are you there, to be viscous, to be thick. So then the first one will now be kerosene. So kerosene followed by glycerine followed by grease. So this is in order of increasing viscosity. So let's see the options. Option A, glycerine first, wrong. Glycerine, grease, and kerosene, wrong. Option B, glycerine first, wrong. Option C, grease, kerosene, grease first, wrong. You are looking for grease last and kerosene first. The option D, kerosene first, glycerine second, and grease third. So option D is the correct option. Option E is wrong. So option D is the correct option: kerosene, glycerine, and grease. All right. So let's go to number 43. Now 43, we're given a diagram. Don't forget option 4. Now 42, option D is the correct answer. Now for number 43, we're given a kind of a beaker this way, and we're given this. I want you to see the diagram. 1, 2, 3, 4, and 5. Those are tubes. So we have this way, this way, with this. Trying to sketch the question out. Then we have this way for 2, like the other way. Then we have this way. Okay. Then for tube 3, we have this way. We have this with this. Then for tube 4, we have this curve here. This one still maintains same level. Here. Then we have this. Okay. They now say these are two. They say call this one Roman figure 1, Roman figure 2, Roman figure 3, Roman figure 4, Roman figure 5. Okay, they said the diagram below shows 5 tubes dipped in mercury. There's mercury here. Say there's mercury here. There's mercury. This is mercury. Okay, this is mercury. So they now said the diagram below shows 5 tubes dipped in mercury. This is tube 1 in mercury, tube 2, tube 3, tube 4, tube 5. Inside a trough of mercury. Which of them shows the correct meniscus and level of mercury? Okay, for when you have a container like this that contains mercury, and you carry a tube, just like a test tube in chemistry lab, either or in physics lab, and you dip it inside this beaker containing mercury. Okay, are you there? So what you will get, if this is your beaker containing mercury, a beaker containing mercury, and you dip a tube inside it. Let's say, let me increase the level of mercury. So I dip a tube, are you there? A test tube inside it. Okay. What we see that is what we see is this. You find that the level of mercury inside this tube will go down. So it can go down up to this place, up to this point. What is the level? Okay, it will go down. The level of mercury inside the tube will not rise. It will go down. And when it goes down, the surface of the mercury will be convex to air. Will be like this. Will be convex to air. Look at it. To convex to air. That's convex to air. Concave to air is like this. Convex to air is like this. So if it is water, the level of water inside the tube will rise. If it is water, the level of water inside the tube will rise, and it will now be like this. It will be concave to air. Are you there? But if this mercury, which we are into now, the level of mercury will convex to air. So this is what we are looking for. The tube that has something like this. Look at it. That's Roman figure 4. It has something like this, and the level of mercury, that is the level of mercury inside the tube, is below the level of mercury inside the container. The level of mercury inside the tube is below the level of mercury inside the container, which is this one. The level of mercury inside the tube is below the level of mercury inside the container. Is that taken? All right. That is Roman figure 4. So option A, I. Option B, I. Option C, I. Option D, IV. Option E, V. So option D is the correct answer. Roman figure 4, IV. And why is it so? Why is it that the level of mercury in the tube is below the level of mercury inside the container? The reason is because the cohesion of mercury is greater than its adhesion to glass. Are you there? So let me repeat it. The reason is because the cohesion of mercury inside the cohesion of mercury is greater than the adhesion of mercury to glass. Cohesion is a force of attraction between the molecules of the same substance. So, and while adhesion is a force of attraction between the molecules of different substances. So, the force of attraction between the molecules of mercury itself, the force of attraction between the molecules of mercury itself is more than the force of attraction between the molecules of mercury and the molecules of the glass container. Okay, so the opposite is for water. The opposite, and what I told you there on that cohesion of mercury is greater than its adhesion to glass, also responsible for the reason why mercury does not wet glass. Mercury does not wet glass. So the opposite of what I said is for water. If it is water, the adhesion of water to glass is greater than its cohesion, and that's the reason why water wets glass. All right, that's number 43 is D, IV. So let's go to number 44. For 44, it says, which of the following statement is correct about Niels Bohr? Which of the following statement is correct about Niels Bohr's postulate of the atomic structure? We all know that Niels Bohr, we know his contributions towards atomic structure. Niels Bohr is one of the scientists that contributed to the development of atomic structure, that we can see the topic in chemistry or in physics. Okay, so which of the following is correct about Niels Bohr? Option A, the one that is correct. Option A, atoms absorb energy when electrons fall from higher orbit to a lower orbit. atoms absorb energy when electrons fall from a higher orbit to a lower orbit. That is wrong. That's wrong. Whenever, let me use, there are for nebula, generally in science, in chemistry, or in physics, we have shells. We have shells, the K shells, the L shell, K shell, L shell, M shell. Are you there? And this shell, around this shell are what are the directions of electrons. Directions of electrons. So we have the K shell, the L shell, the M shell, like that. So this is the direction of the electron. The electrons move around the nucleus here, move around this. This is a part. This circle you are seeing is a part of the electron. It is imaginary. It's not real. Are you there? These are the electrons are just moving this way. So when you trace the part of the electrons, it becomes the shell, K shell, like that. Some electrons also move around this, around the L shell. Are you there? This circle you are seeing is imaginary. It's not real. It's not real. Just like if I take this book now, like this paper, and I fold it, as I folded it now, and I turn it this way. You can see that it's moving in this particular way, but that part through which it is tracing is not real. It is virtual. Okay, but to make it a sense in reality, you just draw circle. Okay, now each this circle represents, according to nebula, this circle represents energy level. Are you there? According to nebula, so the circle is called orbit or energy level. So it can be represented by straight lines. Okay, this second one, maybe this third one, M will be this. When you are drawing the energy levels, the space will be becoming smaller. As you are drawing the energy levels, the space will be becoming what? Smaller. Are you there? Becoming smaller. Are you there? So now, electrons are here. Electrons are the first energy level. Electrons are at the second energy level. Electrons are at the third energy level. Okay, so when electrons move from a higher energy level to a lower energy level, it will release. When the electrons move from higher energy level to a lower energy level, are you there? So they will release energy in form of radiations, energy in form of light, energy in form of pulse of light, flash of light. So but when they move from a lower energy level to a higher energy level, lower energy level to a higher energy level, maybe from N1 to N3, are you there? They will absorb energy. So you will not see any flash of light. You will not see any emission of radiations. Are you there? And that's what we call absorption spectra. Okay, singular is absorption spectrum. So when it moves from a higher energy level to a lower, let's say from N3 to N1, are you there? So they will release energy. In form of radiations, and that we call emission spectra, plural, while emission spectrum singular. Okay, option A says atoms absorb energy when electrons fall from higher orbit to lower orbit. Wrong. When they fall from higher orbit to lower orbit, they do not absorb energy, but they rather release energy. Option B, electrons are restricted to a particular orbit. Yes, electrons are restricted to a particular orbit. Are you there? You can have some electrons there. 2. Are you there? For example, if I have it as sodium is 11, and that's 281. So for this particular K shell, I have 2 electrons. For the L shell, I have 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Are you there? For the M shell, I have only 1 electron. So we have 2 electrons on the K shell, 8 electrons on the L shell, then 1 electron on the M shell. The same thing, we have electrons there, 2 electrons there, 8 electrons there, 1 electron here. Are you there? So 2 electrons there, 8 electrons there, 1 electron. So a number of electrons are restricted to a particular energy level, or particular orbit, or particular shell. Are you there? So, and they have definite energy. We come to that. So option B, electrons are restricted to a particular orbit. That one is correct. Okay. Others are wrong. Well, let me just explain further. Option C, electrons lose energy by radiation. Electrons lose energy by radiation when in a particular orbit. Yes, electrons lose energy by radiation, but it is not when they are in a particular orbit. It is when they move from one orbit to another. Electrons don't lose energy. They don't lose energy. They don't absorb energy. Not until there is a transition. Not until there's a movement. So they will move from one energy level to another energy level, whether up to down or down to up. There must be transitions. Okay, that option C is wrong. Option D, energy gain or loss is in the form of heat. The energy gain or loss when they are jumping from a high energy level to a lower energy are radiations. They release radiation in form of light. In form of light, not in form of heat. And that's why this one is, for example, look at your fluorescent tube. Your fluorescent tube is a good example. The gas inside the tube, it has atoms either, and each of the atoms have electrons. They have electrons that revolve around the shell. So when you switch on the mains, when you switch on the fluorescent bulb, what happens is that current flows into the fluorescent tube. Current flows into the fluorescent tube, and when current flows into the fluorescent tube, the current, it will be in form of electric energy. So that electric energy will be absorbed by the electrons of the gas inside the tube. So the function of the energy absorbed by the electrons of the gas inside the tube is that they will be energetic. They will move from a lower energy level to a higher energy level. So when they move from lower energy level to a higher energy level, at the higher energy level, they are unstable. Are you there? So they will not jump back. They will jump back to their previous state. They will jump back to a lower energy level. When they jump back to a lower energy level, energy is emitted in form of radiation, and that radiation is light that you see. See that, your fluorescent tube has light up or has lighted up. So when you just switch it on, it lights up. Are you there? So it's in form of light, not in form of what? Heat. That's why option D is what? Wrong. Option E, energy is emitted when electrons jump from lower orbits to higher orbit. From lower orbit to higher orbit, energy is not emitted. Rather, energy is what? Absorbed. So option B is the correct answer. Electrons are restricted to a particular orbit, according to Neboa. And other postulates of Neboa are that the energy is quantized. Another postulate is that the angular momentum of the electron is quantized. I said energy of the electrons. Are you there? Energy of the electrons are just like quantized. Are you there? That is, they are specific discrete of energy. Are you there? Then the angular momentum is also what? Quantized. Those are the other postulates of Neboa. Now 45. Which of the following is not a product of radioactivity? When a radioactive substance disintegrates, it emits radiation spontaneously, naturally. You don't need to eat it either, like uranium. It just emits radiations naturally, spontaneously, without being eaten. Okay, and we have many radioactive elements, right? Like that, we have uranium, we have thorium, we have like that. There are many. So these radiations they emitted are alpha particles, beta particles, alpha particles, either beta particles, and then gamma rays, and gamma rays. These are the three radiations that are emitted by any radioactive substance during disintegration or during decay. So experiments show that alpha particles are helium nuclei. Alpha particles are what? They are helium. Helium as an element in the periodic table. Either the second element, hydrogen, helium, second element. So experiments show that beta particles are electrons. Experiments show that beta particles are what? Electrons. Then gamma rays, the scientists have not discovered what they are, what they really are. Either what they really are. So these are the radiations. So the answer, which of the following is not a product of radioactivity? A, alpha particle, that one is there. B, beta particle, that one is there. C, gamma rays, that one is there. D, heat. Yes, heat will be released when a radioactive substance disintegrates during nuclear fission or nuclear fusion. Either during nuclear fission or nuclear fusion. Nuclear fission is when a radioactive substance, when the nucleus of a radioactive substance disintegrates or decay to approximately half of its original mass. Either disintegrate into different products, either into two relatively light nuclei with the release of energy in form of heat. And nuclear fusion is when two light nuclei come together, as the fusion of, let's say, deuterium and tritium. The fusion of deuterium and tritium, either. So you can have a particular product, you can have helium with the release of what? Energy. I don't want to go much into that, but what I want to say, in radioactivity, energy is released, whether fusion or fission, in form of heat. So this is correct. Option E, S-rays. So S-rays is not in any way one of the products of radioactivity. S-rays are produced in S-ray tube. So option E is wrong. So 45 now, which of the following is not a product of radioactivity? So now 45, the correct option is option E. Now 46 is a calculation question. Let's go for that. Options. Okay, number 46 now. 46. A certain radioactive substance has a half-life of 30 minutes. If the count rate was observed, a certain radioactive substance has a half-life of 30 minutes. If the count rate was observed to be 300 after 90 minutes, determine its count rate at the beginning. You can use short method, you can use formula method. You can use formula method and non-formula method. Let's use the non-formula method to save our time. Non-formula method. So nothing like say, okay, let's use the non-formula method. So when it comes to calculation under radioactivity, the starting point is 0. Are you there? So at the zero time, what is the count rate of the radioactive substance? What is the mass of the radioactive substance? Are you there? What is the weight of the radioactive substance? Are you there? So what are the number of atoms in the radioactive substance? Let's assume it is capital letter N. Initially, when it has not disintegrated, when it has not decayed. Okay, so you must start with is at 0 time. It's very important. At 0 time, it has N number of atoms, or it has capital letter A as count rate, or it has M as mass initially. But they said they are using count rate here. You can use capital letter A to represent count rate. That is number of atoms in the radioactive substance per unit time, in a particular time. You can use capital letter A. You can use any alphabet of your choice to represent the count rate. Okay? So we must start with at 0 time. At the 0 time, the count rate is A. Now, the half-life, they say, has a half-life of 30 minutes. That is, you'll be repeating that 30. That is, at 30 minutes, what is the count rate? It will decay to half of its original mass. Original A, it will decay to half of this. Okay, half of this. At another 30 minutes, that's half-life. According to the question, it decay to half of this, A over 4. At another 30 minutes, it will decay to half of the previous one, A over 8, like that. Okay, in that order. So now they said a certain radioactive substance has a half-life of 30 minutes. I've done that. If the count rate was observed to be 300 after 90 minutes, that means we are stopping at 90 minutes. So let's add from 0 to this, from beginning to end. We are going to get 90. So 0 plus 30 plus 30 plus 30, that's 90 minutes. So we have to stop at this particular point. After 90 minutes, you have to stop at this particular point. That's the meaning of that 90 minutes. He now said, if the count rate was observed to be 300 after 90 minutes, that means this is equals to 300. That's the count rate. So if the count rate was observed to be 300 after 90 minutes, that means A over 8. That means your A over 8 is 300. Okay, so make A the subject. So A equals to, multiply, that's 2400. So don't forget that this A is our starting point. Okay, so the gun says determine its count rate at the beginning. Count rate at the beginning is capital letter A, and that's what we have gotten as 2400. 2400. So this is the count rate at the what? Beginning. So options. Option A 600. Option B 900. Option C 1200. Option D 1800. Option E 2400. So that's the final answer. Option E 2400. Okay, let's go to number 47. Number 47 says, which of the following energy conversions takes place when a nuclear reactor is used for generating electricity? Energy conversion takes place in a nuclear reactor. In a nuclear reactor, you have different stages, different processes. You have your uranium. They usually use uranium. So the uranium will be in a kind of a lump form, and it will be grounded into a powdery form, to increase the surface area. So do you understand? So now the conversion goes this way. We have the nuclear energy, which is energy possessed by the radioactive substance. For example, the radioactive substance in question could be uranium. So nuclear energy possessed by it. Okay, now by the time it decays, it releases energy in form of heat. It releases energy in form of heat. Okay, now it releases energy in form of what? Heat. So the heat that is released, will be used to boil, to produce steam. Are you there? The heat release will be used to produce steam. We used to boil treated water, deionized water that has no ions, pure. Are you there? So the heat release will now be used to boil water. Are you there? So water boil will produce steam, and the steam will now go and turn the turbine. The turbine is situated in between, around magnetic field, around magnets. So it's a complex process. Okay, so when the turbine turns, that is mechanical energy. Are you there? That is what mechanical energy. And don't forget, we are coming from nuclear energy, from the radioactivity that produce heat, which is heat energy. So from, you have the nuclear energy. So nuclear energy from the radioactive substance, e.g. uranium, to go to what? Heat energy. To heat energy. The heat is used to boil the treated water to produce steam. Are you there? The steam will not go, and the power, that steam is under high pressure. The steam will be under high pressure. That is very powerful, that will be able to turn the blades of the turbine. Are you there? So when it turns the blades of the turbine, the turbine begins to rotate, begins to move around. So, and the movement of the turbine round is mechanical what? Energy. Mechanical energy. When the body is moving, that's mechanical energy. So, mechanical energy. Mechanical energy. Okay, that's what? Mechanical what? Energy. So, the mechanical energy either is situated, the turbine which possesses mechanical energy is situated around magnets either, and as it moves, it cuts magnetic lines of force. It cuts magnetic lines of force of the magnets surrounding it, and when it cuts magnetic line of force, an EMF is induced. An EMF is induced according to Faraday's law of universal gravitation. So according to Faraday's law of electromagnetic induction, so to say, according to Faraday's law of electromagnetic induction, so an EMF will be what? Induced. Are you there? An EMF will be what? Induced. So, and the induced EMF constitutes the movement of current. The induced EMF is a measure of current, and current is what? Electric energy. Electric energy. So for mechanical energy, we have it to what? We have it to electric energy. Electric what? Or electrical energy. We have it to electrical energy. Okay. So, or electricity. Okay. So now where are the options? Option A, heat. It says which of the following energy conversion takes place when a nuclear reactor is used for generating electricity? Option A, heat to nuclear to electricity. That's wrong. So we are not starting from heat. Option B, heat to mechanical to nuclear to electricity is wrong. Don't start with heat. Are you there? Option C, mechanical to heat to electricity. No, don't start from mechanical. Option D, nuclear to heat to mechanical to electricity. That's the correct answer. Option D. Option E is wrong. Option E, nuclear, mechanical, then heat, then electricity. Heat cannot produce electricity as far as the stages are concerned. Are you there? So it is a mechanical, the motion of the turbine that is cutting magnetic force that will induce EMF, which is a measure of the current or electricity. So option D is correct. Nuclear to heat to mechanical to electricity. That was number 47. Option D, correct answer. Let's go to number 48. 48. Number 48. An atom radiates energy of 2.928 times 10⁻⁻20 joules when its electrons falls to the ground state. I've explained this one before. Are you there? The analysis that according to Nebua, when an electron moves, jumps from a higher energy level to a lower energy level, higher energy to lower energy level, energy is released. Are you there? So an atom radiates energy of 2.928 times 10⁻⁻20 joules when its electrons falls to the ground state. The lowest energy level is the ground state from a higher energy level. So calculate the frequency of the emitted photon. You calculate the frequency of the what? Emitted photon. So the formula is E equals to HF. Can we list out the parameters first? Let's look at the parameters first. The energy is 2.928 times 10 raised power of -20 joules. That's the energy. An atom radiates energy of that in joules when its electrons fall to the ground state from a higher energy level. Calculate the frequency of the emitted photon. Frequency is F, question mark. Then we are given the small letter h. We are given small letter h as 6.6 times 10 raised power -34 joules seconds. That's the Planck constant. So the formula to calculate the energy released or absorbed here is E equals to HF. Okay, that is the formula. Energy is equals to Planck constant multiplied with what? Frequency. So when you substitute, right there, you have energy is 2.928 times 10 raised to power minus 20 equals to the Planck constant 6.6 times 10 raised to power minus 34 multiplied by our frequency. So making F the subject, so F equals to 2.928 times 10 raised to power minus 20 over 6.6 times 10 raised to power minus 34. Okay, when you use the calculator for that, let me get my calculator is there. Okay, calculator for that, we have that F, the frequency equals to, I would like to divide these numbers first before this. That's 2. If you want to use a calculator, some calculator, you put this one, the numerator in bracket, divided by the denominator in bracket. So 2.928 divided by 6.6, and that has given us 0.444. Then times 10 raised to power. Indices for the minus 20 plus 34. This one goes up, indices, and that is what? 14. That's 14. Or you use the calculator to divide it direct, either you get this particular answer. Take the standard form. F equals to 4.44 times 10 raised to power 13, because that one is minus 1. When you go this way, minus 1. Take that minus 1 from 14, you have 13 as. Okay, that is the answer to that. So let's look at the options. Option number 48, question number 48, option A, 1.93 times 10 to the minus 12 hours. Wrong. Option B, 2.90 times 10 to the power 13 hours. Wrong. Option C, 4.44 times 10 to the power 13 hours. That's our correct answer. All other options are wrong. So don't forget that the question says an atom radiates energy of 2.928 times 10 to the minus 20 joules when its electrons fall to the ground state from a higher energy level. Calculate the frequency of the emitted photon. Given the Planck constant. So 48, correct option is option C. Now 49. So let's go. 49 is a calculation question. Okay, 49. It said electrons are liberated when a metal is illuminated by light of, that is photoelectricity. So when a metal is illuminated with light, either it emits electrons. That's photoelectricity. So, and that's the principle that is used in solar cells, either solar cells, solar panel, and all that. So electrons are liberated when a metal is illuminated by light of wavelength 4.0 times 10 to the power minus 7 meters, and that is the wavelength of the light, wavelength of the incident light, wavelength. Let's say lambda subscript L, wavelength of the light is 4.0 ordinary 4 times 10 raised to power minus 7 meters. That's wavelength of the light, of the incident light. That is the wavelength of the light that is coming from the sun. If the maximum energy of the emitted electrons is 1.95 times 10 to the minus 19 joules, maximum energy of the emitted electrons. So energy of the electron, let's say it is capital letter E, subscript small letter e, energy of electrons, maximum energy of electrons. Let me take it as EE, and that is 1.95 times 10 raised to the power of minus 19 joules. That's energy of the emitted electrons. Now calculate the work function of the metal. Work function of the metal, let me represent it by what? Capital letter W equals to question mark. Okay, capital letter W equals to question mark. So, and we are given H, we are given Planck constant as 6.6 times 10 raised to the power minus 34 joule seconds. We are equally given the speed of light, small c, as 3 times 10 raised to the power 8 meters per second. You know, the basic principle behind this is this: the energy of the incident light, the energy from the sun that is falling on the metal is equal to the energy of the electrons released. Electrons will be emitted from the surface of the metal. So is equal to the energy of the electrons plus the work function of the metal. Work function of the metal is the internal energy processed, to a layman definition, is the internal energy processed by the metal itself. The metal itself has an energy barrier, has a kind of a barrier that the electrons inside it must surpass before they can be released. It's just like activation energy in chemistry, that is responsible, that it must be surpassed. The activation energy must be what? Overcome before a reaction can take place. So the same thing here, work function is the minimum amount of energy that must be overcome before electrons can be emitted from the surface of a metal when it's illuminated by light. So energy from the light, that's capital letter E subscript L, energy of the light equals to energy of the electrons plus the work function of the metal. So the sum of these two must be equal to this, according to Albert Einstein. Okay, so this is Albert Einstein photoelectric equation, in case you are asked. Albert Einstein photoelectric what equation. So normally we are not given the energy of the light. You can go back to the formula I've used for energy equals to HF. Okay, energy equals to HF generally. So energy of the light, we use HF. Okay, and we are not given the frequency of the light. Frequency of the incident light is different from frequency of the metal itself, work function. So HF, we're not given frequency. We replace the frequency with, remember that, let me write this, energy of the electrons plus work function. Okay, now the frequency of the light, of the incident light, is not given in the question. And go back to waves, we have V equals to F lambda, right? So our V now, V as far as this question is concerned is C, or this topic is concerned is C. They are given C. Can you see that? That's why they gave you C. C is the speed of light. Using that as V here. That's C equals to F lambda. Are you there? So from there, let's make F the subject. So we have C over lambda equals to what? F. So we now come here and replace the frequency. Since we are not given frequency, we now replace frequency with C over lambda. So that is Hc over what? Lambda equals to energy of the electron plus the work function. So we have derived the formula. This is the formula now. So we now go and substitute. The H is the Planck constant. It's given as 6.6 times 10 raised to the power minus 34 multiplied by the C, speed of light, is given as 3 times 10 raised to the power 8 all over the wavelength. The wavelength of the light is given as 4 times 10 raised to the power minus 7. Okay, so all equals to the energy of the electron. Energy of electron is given, that's EE, that's 1.95 times 10 raised to the power minus 19, plus, we're looking for the work function, plus W. So you find the work function. I said calculate the work function of the metal. So this is what you're going to do. You just bring up your calculator and begin to press. Let's solve this one first. That is the energy of the light. That is 6.6 multiplied by 3 equals to, divided by 4 equals to, that's 4.95. Let me write it here. 4.95 times 10 raised to the power what? Minus 34. Minus 34 plus 8 indices. Minus 34 plus 8, that is 34 minus 8. That's minus 26. Minus 26. So minus 26, this minus 7 here will come up and become plus 7. So minus 26 minus 26 minus 26 plus 7, minus 26 plus 7, and that is 7 minus 26, and that gives us minus 19. So 4.95 times 10 minus 19 is the total answer for this side. So equals to, what was our, equals to 1.95 times 10 raised power minus 19 plus W, plus W. So making W the subject, we have 4.95 times 10 raised power minus 19. Take this one to the other side, the sign will change, minus 1.95 times 10 raised power minus 19 equals to the work function. So they have the same indices. So just subtract only the only the figures. 4.95 minus 1.95, and that's giving us 3. That's 3 times 10 raised power minus 19 joules. That is our W, the work function. That's the work function. Okay, it's interesting. It's interesting. Yeah, this is interesting. This is interesting. So let's look at the option A. Let me repeat the question again. Electrons are liberated when a metal is illuminated by light of wavelengths 4.0 times 10 to the minus 7 meters. If the maximum energy of the emitted electrons is 1.95 times 10 to the minus 19 joules, calculate the work function of the metal given Planck constant and speed of light in air. Options. Option A, 2.1 times 10 raised power minus 20. Option B, 3.0 times 10 to the minus 19 joules. That's our answer. Option B. Option C, D, E, they are wrong. Option C, 6.9 times 10 to the minus 19 joules. Option D, 8.8 times 10 to the minus 15 joules. Option E, 2.5 times 10 to the minus 14 joules. So the correct answer is option B, 3.0 times 10 to the minus 19 joules for number 49 of this physics NECO. Now number 50. Let's go to number 50. Okay, we are approaching number 60 gradually. Number 50. Number 50 says, which of the following equations is an equation of the uncertainty principle? Let me just write the options. Uncertainty principle. That is Heisenberg uncertainty principle. Heisenberg uncertainty principle states that it is impossible to determine simultaneously. It is impossible to determine simultaneously on an atomic scale the position and momentum of a microscopic substance, particle. Are you there? It is impossible to determine simultaneously on an atomic scale the position and momentum of a particle. So it is only the product of the position and the momentum that is greater than or equals to the Planck constants. That is Heisenberg uncertainty principle. I've explained the I've stated the law, okay, or the principle. So look at the options. They gave us option A as change in E dot change in V greater than or equals to H. Option B, change in E dot change in S greater than or equals to H. Option C, change in V dot change in P greater than or equals to H. Option D, change in X dot change in P greater than or equals to H. Then option E, change in X dot change in T greater than or equals to what? H. So the E, let me explain. The E represents energy. The V represents velocity. The P represents momentum. Of course, the T represents time. So, and we have complementary